I think the question is, evaluate this integral using polar coordinates. So in using polar coordinates, I think, I don't know you guys, I think the first thing I should do is draw a picture. Because I think to rewrite this integral using polar coordinates, I need to know the region over which I'm integrating. And so drawing a picture of this, you guys help me with this. With that function in Lagrange position, what does it look like? Good, we don't care. To come up with the region described by my bounds of integration, I'm going to go over here. So x ranges from?
Zero.
Nothing. I think it's y ranging.
Yeah.
This is my first variable integration to y. I think y is ranged from y equals 0, which is the x-axis, to y equals the stuff, which is, I don't know. Just give it a name.
Y squared.
Let's give that thing a 2x squared, or 2x minus x squared, the name of y, which is what it is. Let's clean it up to make it look pretty. I think that means y squared is equal to this. Or does that mean x squared plus y squared is equal to 2x? Well, let me bring the 2x over. Well, let me bring it over legally. And let me complete the square on x. That means I'll add 1 to both sides. But jeepers, you guys, doesn't it just simply give me this? X minus 1 quantity squared plus y squared is equal to 1. That's just simply a circle whose center is located at 1, 0, and whose radius is, well, the 1. Whatever is squared to generate that constant term. And so I think, did I say circle? I misspoke, didn't I? I meant semicircle. I've only got half of it. Big dot. And so I think this is the region over which I'm integrating. So diving in and rewriting my bounds of integration, I think the R values, if you guys draw just an arbitrary red ray emanating from the origin through any part of that shaded region, no matter where the error is, I think R ranges from 0 to something. It's just the something is the terminal point on the arrow, but that's just simply on a circle. So I need to take another break, excuse me, come back over here and re-express this rectangular equation back in polar form. You guys, this one looks easiest for me. Can I just that down here? Because I think with this equation, that simply says the left-hand side is this. The right-hand side is going to be 2 times r times the cosine of theta. Since I already know that r being equal to 0 is my lower bound of integration in terms of r, can I just divide by it? And that's merely going to give me as my upper bound of integration of, sorry, is that my 2 cosine theta? You guys, am I getting too sloppy? That's the theta. Now, as far as my theta values are concerned, well, check out the range of theta values for the arrows that span that shaded region. I think my theta values span from a low value of up to a high value of pi over 2, so I'm integrating from here to here. Now, taking a peek at what you see in integrand's position, I think the r needs to be, excuse me, I'm talking too fast. I think the x needs to be replaced with r cosine theta. It's just that my dy dx is replaced with r dr d theta. Doesn't that give me, collectively speaking, an r squared cosine theta dr d theta? Help me, yes, no?
No.
Okay. Well, you guys happy in the case? I want an honest answer. Jeez, do you need to see me finish?
No.
Okay, so you can integrate. Why do you think that was that big?
Good question.
Yes.
How is it only the top half of the circle?
Because when you take a peek at y being equal to the principal square root, you see no plus or
It's
minus.
just the
That's why it's a
I see.
semicircle, not a full.
I see.
I don't know why, but you marked me off a point for no reason. Like, not that I can see. You cross off a 2 and then put y, and then it's actually correct. So I don't understand why. And then you put 6 pi over 2 at the bottom. So yeah,
Where does the 6 pi over 2?
at the bottom right, right there. That's it.
No, that's equals pi over 2. Equals pi over 2. By the way,
Okay.
where did you come from?
Oh, I thought it's from this point, and then you also have to include the second.
I don't see it anywhere in the second block.
Okay, but so was it just because my drawing's wrong? Because
Oh, yeah.
I was because I guess I was insinuating that you had to include the other part by multiplying by 2.
And I really attacked you on the 2 because the 2 shouldn't be there.
Oh, so it should just be pi over 2.
Yes, that is your final answer.
Oh, okay.
All right. Can we do something different today? Actually, I'm gonna get caught up today. I don't wanna be finishing semester rushing. So I wanna finish this section and talk about what's upcoming in the next section. That being the case, when I come to class on Friday, you guys, I'm going to be discussing section, in class on Friday. The last section is chapters 13.7. So you guys, Friday when I come to class, this is when I'm gonna start them. This is when I'm gonna start them. This is when I'm gonna start math 32. Because I think this is the only first real section. So I officially start class on this upcoming Friday. So for Friday and every single day remaining in the semester, do you think you could be rather diligent and dive in and read ahead of me? Because here's where, I don't think the course is difficult, I just think it might be challenging. So keep ahead of me. Meanwhile, it's a fancy way of committing to U subs in higher dimensions. We call them Jacobians. Or sometimes I say, I'm going to apply a Jacobian transformation. It's where sometimes it might be really difficult to dive into. But if I apply the kind of transformation, which typically is a nonlinear one, then the integration becomes more easy. Very much like saying, oh, I got an integral in terms of x's and y's and z's, and it's too difficult to integrate. Maybe converting to, I don't know, cylindrical, or what today we're going to discuss, spherical coordinates makes your life a little easier.
So, for 13.7, I don't have my book right in front of me. What's that called?
The official title, I don't know if he calls it Jacobian transformations,
Okay.
or if he just calls it transformations in two space. Let me look.
Do you know how,
Besides, you might be using a different book.
do you know how far we're gonna go before next test?
I don't even know when our next test is.
So wait from Friday?
So it's next Friday.
Yeah.
By the way, the section 13.7 is called change of variables in multiple integrals. So next Friday?
No.
I don't know. Might be 14.2.
Okay.
It might be. What's that?
How are we gonna get there in 2 days? We're almost done with the chapter.
Well, you know I'll be done with this chapter on Friday. It's just on Monday, I should be coming to class discussing section 14.1, but you guys, it's just a section entitled vector fields, and it's typically just visual, and I think we can dispense on it pretty darn quick. So I don't think 14.1 is sophisticated at all.
What's 14.2 then?
Oh, something beautiful.
Very sophisticated then.
Line
It's the cover of
integrals.
your book. It's talking about some kind of curve in an XY coordinate plane. Been looking at a fence coming up in 3 space and computing the area of the fence, or at least on one side. Sounds goofy, sounds useless, but in application becomes tremendously important. And maybe from the line integrals, I'll be able to generate some different versions of your fundamental theorem of optics. Green's theorem, divergence theorem.
What's Green's theorem?
It's a way to rewrite a double integral in terms of a line integral.
What is,
Really slick stuff.
does Green's theorem have anything to do with
No.
Green's formulas?
No.
All right.
Sorry, he's a math 33. The guy just got it right.
Yeah.
His math 33.
You do math, so you got the math next semester.
Yeah, if you guys are interested, that discrete math course is already online. It's Fridays from 9 to 1:05.
We need 20 people.
The college is being very mean to us. It's not giving us typical rules. It's saying we gotta satisfy higher rules. So keep that in mind. And the class is not gonna be taught where you see the professor talking 4 hours straight. The professor will reorganize things, so it's not quite that boring. I'm just saying, it's 4 hours on Friday. And don't expect the professor to come in and just talk for 4 hours.
Because you want to kill yourself. It's miserable.
That's a lot.
Oh, no, it's not you. It's just, after like 2.5 hours, your eyes glaze over and you begin to think of better things.
What better?
Anything not lecturing. Yeah, exactly.
I taught for the years of Math 33 for 3 hours a night, for 2 nights a week. It was really, wow, excuse me, man.
How the test scores come out?
Much better.
Yeah.
Wait, are we doing math?
3-hour test.
What's that?
Are we doing math calculations today?
Oh, yes. Let me talk about spherical coordinates first. X-axis, Y-axis, Z-axis, everybody. We've already talked about locating positions in 3 space using rectangular coordinates. We've even gone into cylindrical coordinates. Let me approach it a completely different way. Because I think I can do something different. I think to locate a point in free space, what I could do is walk a certain distance from the origin straight there. And let me talk about the distance being rho. It's just that with an arbitrary point in free space, I can identify two angles. Number one, take this point in free space, drop it straight down to the x, y coordinate plane. And take a peek at the angle you're making with the positive x-axis. I'll call it theta. Now I need one more identification, one more parameter to identify that point in free space. So I'll talk about the angle I'm making with that ray going from the origin of that point with the positive z-axis. I'll refer to this phi. So when you take a peek at my picture, just to make sure everybody sees this, that angle theta lives in what coordinate plane?
X,
XY. The angle phi lives in what coordinate plane? I can't hear you. I don't think it lives in any coordinate plane. Well, I might get lucky, but in general it doesn't. I think phi is the angle that this ray from the origin connected to that point in free space makes with the positive z-axis. It's not necessarily an angle in any of my coordinate planes. Did you guys get that? So I think then the point x comma y comma z located right here could also be interpreted as a position in which I've got a distance traveled from the origin to get there. The angle I make in the xy coordinate plane, if I took my point x, y, z, projected straight down the xy coordinate plane, the angle I make down there with the positive x-axis, comma, the angle phi, which is the angle I make with the, with that ray emanating from the origin, getting to that point, that I make with the positive z-axis. You see if this makes sense. What's the graph that look like? What does a graph that look like?
That's a plane right here.
Yeah, I think it's just a plane that's anywhere. Make a fuller sentence. Flat, which means I'm parallel to the xy coordinate plane. I think it's a nice way of stating it. What do you think this looks like? I mean, with what I described in terms of polar coordinates, what is it? Sphere with radius. Very nice. I think it's just a sphere of radius 1 because I did not identify theta or phi. They could be anything. And so I think all the points of the origin, all the points that are 1 unit from the origin constitutes a sphere.
Is that E associated with eccentricity?
Ooh, that's not an E, sorry. It's a Greek letter rho. Sorry, it's not E. It's not with this constant.
Oh, because rho usually looks like a sideways P thing.
Yeah, that to me looks like a sideways thing.
Okay.
It has nothing to do with eccentricity. We're not discussing the conic sections. What does the graph of this look like?
Also a sphere.
Oh, it's the same thing, but my arm got worn out. I wrote too much. Do you see how nice that is? Ooh. The what? Yeah, theta equals it's a plane. And the angle theta is the dihedral angle I make with the xy coordinate plane. Ooh, how about this one? Maddie? I didn't hear you. Yeah, I think it's a cone because the angle I make with the z-axis is fixed at positive 1 radian, but I didn't tell you what theta was, and I didn't tell you how far to walk. So I do think it's a cone. In my picture, let's talk about relationships. Let's talk about how I can come up with x, y, and z in terms of, well, the rhos and thetas and phis. In my picture, can I add something? Since I'm adding, I'll change colors so you can see that I'm adding it. In my picture, if I connected this point right here perpendicularly to the z-axis, wouldn't this be a right angle? Wouldn't this be z? Wouldn't this be r? Well, the r I referred to when I was dealing with cylindrical coordinates. You guys hear me? Here's my angle phi. Isn't the opposite over hypotenuse r to phi? Excuse me, r to rho. But that would be the sine of phi, wouldn't it? But if the sine of phi is r over rho, doesn't that mean that r is equal to rho times the sine of phi? Oh, there's something else in there. Check this out. I think when it comes to z, z divided by rho is nothing more than the cosine of phi because that's the adjacent side to phi to the hypotenuse. And if the cosine of phi is z over rho, doesn't that mean that z is equal to rho times the cosine of phi? And just like with cylindrical coordinates, you guys, it is the case that x is equal to r times, just like with cylindrical coordinates, the homework you did for today. No, humor me. X is equal to r times the cosine of theta. And y is equal to r times the sine of theta. Oh, you guys, I made a mistake. Well, maybe not a mathematical mistake, but I think I wanted x, y, z represented in terms of z's. And I got an r in there, so I'll switch it out. I think what I'm really trying to say is that x can be represented by r, which is rho sine of phi times the cosine of theta. And likewise, y can be represented as r times the sine of theta, but r's got another name, namely rho times the sine of phi. So rho times the sine of phi times the sine of theta is going to be my spherical representation for the y coordinate. So far, so good, you guys? Yes, please.
Hung up on something. So why was theta equal 1 a plane? Because isn't theta's angle?
Because I think if you fix data at 1 radian, I know what direction I'm looking at in the xy coordinate plane. But I didn't tell you what phi or rho was. So I think looking in the direction of theta, rho could be anything, spanning up and down, maybe down below the xy coordinate plane. I can walk as far as I want. I think clearly with my picture, I shouldn't say clearly, I think with a bit of looking at my picture, you can conclude that theta being equal to 1 has to constitute a plane where rho and phi are not fixed. As long as you believe me. Let's talk about integration. Because I think to evaluate an integral over some region E, in terms of area. Yes, Catherine.
I'm sorry, but can you write rho so it doesn't look like an E? Just because increases
So what should I do? A smaller hoop?
Just do a sideways P.
No.
A sideways P?
Yeah, like, here, let me write it for you.
Like that?
No.
No, that's not sideways P. That's an actual P.
That.
Why?
That's rho.
You rotate that 20 degrees, that's a sign to use the infinity card, isn't it? Catherine, is it really that bad?
Well, I'm trying to figure out how the heck you're going to write it and have it not look like an E, I guess.
What if you have an E in the equation? Then it's just going to look weird.
Okay, how about this? Watch,
So-
watch. I maintain it's definitely not E because that is below the C. You're embarrassing me. Oh, I can't find it. It should be my R.
Oh, see, here's the row, right? So it just looks like a P. That's it, right?
You know, I see your guys' point. I'll be honest with you. I rarely see the type print like that. I mean, I'm actually just drawing the way I'm used to seeing it, even in text. Oh, yeah,
I would normally just do like a P with a little tail, right?
Is that better?
That works, yeah.
That's better. Okay, yeah,
Okay.
It's slowly turning back into an E.
All right, leave me alone. How's that? Oh man, it's gonna be hard to get. Did you guys agree with this though? So watch. Oh, hold on. I didn't do that.
Remember, he grades our tests.
That's true. That gives you the power. So you guys, traditionally speaking, X, Y, Z, is it the case that my upper bounds, if I'm going to integrate respect to Z first, that's a function of X or Y, I forget. Both X and Y. So how about an H2 of X comma Y and an H1 of X comma Y? You guys, when I first introduced this, I may not be consistent. I don't care what function, what you call it function. It's just a function x and y. But I think with my next variable integration being y, I think I've got functions in just x. So what do you guys want as a name for a function here? Yeah, nothing. They're just constants.
So it's always going to be like that. You go from like two variables, so 3 space, 1, 2 space, 1 space.
Well, certainly, because if you're integrating respect to c first, notice that you've got two other independent variables left.
Yeah, but if it's not z, let's say it's x.
Well, that's fine. If this is x, you got a y and a z.
Okay.
Doesn't make any difference. You just reorient yourself in free space. But you and I saw last time in class that I can reinterpret in terms of cylindrical coordinates, where I had my function f in terms of x, y, and z. And we typically integrate respect to z first, and then typically respect to r, and then respect to theta. Did I miss anything?
Yeah.
Yeah, you forgot an R.
Now, I think that's important, because when it comes to cylindrical coordinates, we've got an extra factor of r in here. Where'd that come from?
From your DR.
Well, the volume, that little kind of cubical thing, where I had an arc length for one of the dimensions. And by the way, my bounds of integration were,
I have a question about this.
yes.
Is it always going to be in this order, in what we see, or like?
I hate to say every single time, there are some exceptions, but almost always you'll see it in this order.
Okay, why? Is it just convention?
It's because when I've got a graph, a surface that can be described cylindrically, it's just more convenient to think of the z as a function in r's and thetas. And typically with the polar graph and the SY coordinate plane, typically with their shapes, r is described as a function of theta, not vice versa. Okay. And I think I got a couple functions, h1 and h2, in terms of r's and thetas. And maybe some functions here like, I don't know, a g1 and a g2, which are functions in terms of just theta. And then I've got extreme values for theta.
I think what Eric was asking, like for the test, though, are we going to have something else?
The answer is no. Because remember I said sometimes I have exceptions where I can interchange variables?
Yeah.
Those exceptions tend to be really easy examples.
Okay.
And since they're on the very easy side, who cares? I also maintain, shoot you guys, here's my next step. Are you ready? Because here I go. I got a function f described in terms of how about thetas, rhos, and phis? So like I said over there, another name for the x coordinate is going to be, is that a rho sine of phi times a cosine of
Your
theta?
rows are e's again.
All right. And I think the y coordinates are going to be rhos of sine of phi times the sine of theta. And I even think my z's could be represented as rho times cosine of phi. Oh shoot, you know what? I'm stuck. I'm serious. I'm really stuck. I need to take a break. Take my break. Come over here. Since I'm integrating with respect to volume, I need to talk about the volume of a little tiny slice of the three-dimensional image in free space. So allow me. Here's my x-axis. Here's my y-axis. Here's my z-axis. Let me consider something that kind of looks like this. And we'll talk about such a sliver. You guys ready? Maddie, why are you looking like that? Are you ready?
I was trying to understand why is it not?
Yeah.
Ah, good point. I think I'm all wrong. I think that's the image I use when I describe cylindrical coordinates. I think when it comes to spherical coordinates, things are going to be a little bit different. This time I'm going to be emanating from the origin. So x-axis, y-axis, z-axis. And emanating from the origin, I think I'm going to look more like this. No tricks this time. And if I want to talk about the volume of that little tiny slice at the end, let's talk about its dimensions. I think this dimension right here is just simply going to be a small change in the rho direction. It can be Brad. But I think if I project it straight down to the x-axis, x-axis, I meant xy coordinate plane. I think this is a small change in the theta direction. So this arc length that you and I, like you and I discussed before, is just r times a small change in the theta direction. That's a change in the arc length. But I think that's going to be nothing more than this dimension. There's my r times this change in theta.
About the,
Oh, very nice. So I think right here is going to be a small change for the angle phi. But wouldn't that be its arc length, which is rho, times the small change in the phi direction? I saw the smile. I saw the smile. Oh, you guys, I don't like this. Darn it, it's not going to work. Look, product of these three things involves rhos, phis, and thetas, and oh, look at that r's. So let's convert. I think another name for r is just rho times, I know you can do it,
We're still writing.
sine of my phi. It's my times a small change in theta. And I want you guys to take a picture of the product of these three things, and that will be my representation for the volume of that little sliver using spherical coordinates. Which means in the integrand position, I think I've got some extra stuff in here, you guys. I'm running out of room, I'm sorry. This is times rho squared times the sine of phi. We will typically integrate with respect to rho first, then theta, then phi typically. Sorry, my phis are getting too small. Which of course means rho might be interpreted as a function in both theta and phi. And so the next bounds of integration will be functions in terms of, how about just phi? And finally, v is going to range over one constant to another. That'll typically be how I set up an integral in terms of these cylindrical coordinates. I said cylindrical, sorry. That's typically how I set up an integral in terms of spherical coordinates.
Slow down now.
Yes, I will. I gotta slow down because now I want to dive into some examples.
Yeah, but we have to just look at
You integrate with phi last. Can't see that in the book.
Yes, sorry, typically phi's last. The intermediate variable is typically theta, and typically I integrate respect to rho first. Because typically rho will be a function of those two variables.
It's a lot more complicated.
It does, but the whole point behind this is when you actually dive into the integration process, it's not.
Honestly, it doesn't seem all that much more complicated. Like, integration is pretty easy.
See, guys, I don't mind if you attack me and stop me, but in 35 minutes, do you think I want to try to get through 5
Could you
examples?
read what that says
Yes.
way on the end?
I'm sorry, it's too far away. So, Linda, I got a rho squared,
Okay.
sine phi. And then I'm integrating respect to rho, then theta, then phi.
So the extra part, like the R in the cylindricals, is our p squared sine phi.
Quite the contrary. I think this r translated into a single rho times sine of phi.
That's what I mean.
And there was an extra factor of rho because the arc length relative to this piece of my picture.
Okay, but I'm just saying, we have these extra p's.
We do.
Okay.
And it
so
partially comes from
It's
the r.
rho squared sine
It is
phi.
rho squared sine of phi.
And then,
And then integrate respect to rho, then theta, then phi. I'm sorry if I crammed it in the right hand.
thank you.
So you guys, let's see if I can do just that. Let's see if I can get away with giving you a few, 5 examples today. And if you don't mind, if the integration process is easy, can we skip it? I think the key here is setting up the integrals, identifying bounds of integration. So let's go back to something we've already determined. My very first example will be a simple one. So you guys remember how I told you to make a splash at your next party you go to? Just derive the volume of a sphere. Let's do it again with spherical coordinates.
Oh, that's right, okay. Are you gonna like sneak partial fraction decomposition in here somewhere on the test?
Well, I always try to, yes, of course.
I really don't have to go back and remember how to do that, but should I, would that be a good, just to buy the.
Have I told you the story of my wife's oldest daughter's 21st birthday?
Let's hear it.
Does it have something to do with partial fraction decomposition?
Maybe.
All right.
She went to a party over here right across campus, some apartments. It's a couple of years ago. And they found out she was my stepdaughter. So they threw her in the pool.
Was this Wendy?
No, her oldest is
Yeah,
sister.
because I thought when they just turned 20.
She did.
Yeah.
She's cheering second.
When she's showing him how to drive one of the trails.
No.
Or the steer.
Was it Wendy that they threw in the pool?
What's that?
Was it Wendy that they threw in the pool?
No, her older sister.
No.
So you guys, if I'm going to compute the volume of something using triple integrals, it would not be the case that this function f is
Dot.
So would you
Start
say one
again.
more time?
Yeah, this is important. You
We were
shouldn't
still
hesitate.
thinking it was cool.
Sorry. Get away from the pool. If I'm going to compute the volume of an object using triple integrals, what's this function f? You have the constant function of output is 1. So I think in the integrand's position, I merely have this. Isn't it just my rho squared sine of d? Is that d rho d theta? Got the bracket. D rho.
That V kind of looks like a D.
It is hard to not turn it into an E, but.
I don't think it's that hard.
Shaky. D theta d theta.
Yeah, start at the bottom.
No, but
Start
it
with
turns
the
into so many things.
Yeah.
You open up some older math texts. I think they all type print like I write. They probably changed it because they look like anyway. If I were to draw this region whose volume I'm trying to compute, do you guys mind if I don't? Can I just cheat? Can I just do the upper half? It just might be easier with bounds of integration. So I will compute the volume of the sphere by looking at 2 times the evaluation's integral, where I'm looking at that region 3 space. So humor me. What's rho? Yeah, the radius of the circle. Or excuse me, I misspoke. I meant radius of the sphere. What's the lower bound of integration? 0. What about theta? Excuse me, the fairest of theta. How does that ring? What about b? I can't hear you. 0 to
Pi half.
0 to pi halves. I like that. You guys, in this example, in case you think I'm misleading you, with this one, can we just finish? What should we come up with as an answer? 4/3 pi r cubed. And I think in this particular example, I get 2 times 0 to here, 0 to here. Okay, I'll slow down. Does that give me is that an r cubed over 3?
Uh-huh.
Now integrating with respect to theta. Does that give me this? Is that a 2 times the integral of 0 to pi halves? You guys watch me cheat again.
Professor Valguy,
Yes.
it's Wikipedia, row.
What a Wikipedia?
Wikipedia, row.
What a Wikipedia?
See? But
I have-
Wikipedia's never wrong, so.
You know, I've not once in my life ever gone to that website.
Never gone to
I
Wikipedia?
refuse to go to that website. I think somewhere in my past, somebody showed me something on there mathematical that was so wrong. So wrong. So I understand what the website is, that's why I don't go there. You guys check this out. If I integrate respect to theta, it just gives me a theta factor. If I enter from upper to lower bound of integration, doesn't that just give me another 2 pi? You guys, I know I'm skipping along. Uh-oh, hold up, I made a mistake. I lost my sign. And finally, I'll integrate respect to phi, but that's simply going to give me, well, integrating sine of phi, what do I get? I get, well, negative cosine, don't I? Ranging from here to here. I lost the rest. You guys took my glasses off. Is it 2 pi thirds? Is that an r cubed? And I just simply maintain evaluating negative cosine of theta at the upper bound of integration, just 0. Cosine of theta valued lower bound is going to be positive 1. But I got a negative sign. It's being subtracted. It's just positive 1. Oh, thank goodness. I really do get 4 pi thirds times the radius cubed. It works.
And then by doubling it, the only thing, if we didn't double it, the only thing that would change would be the phi, right? The bounds on phi,
Yeah, and so I suppose you could have avoided doubling it and just integrated from,
0 to 2.
I agree, 0 to pi. I agree. I was just being lazy. You want to be honest?
From the x-axis.
But you guys, are the first ones we ever complained about my rows. I really do think. I could be wrong.
Oh, the E thing is like the R, what did they use for forward?
Oh,
Yeah,
yeah,
they were
you guys,
using
I have a
R
habit of
before.
using E, but you use whatever you want. I'm just saying integrating over some region in three space, I refer to as E. So think of E as a body or a solid in three space. Where E is equal to, how about all the points above this and below this. So you guys, first things first. Don't look at the function due to Grant's position. Let's just you and I talk about the region in three space, the region E. What does that look like?
The first one I think is like a bowl.
What kind of curvature?
Is it a bowl thing?
Concave or convex?
This way.
Concave or convex? Concave or convex?
Well,
Neither?
Neither is going to be.
All right.
It's just a cone.
I'm good at this.
You're good at this. Now you make me laugh. I can't draw a circle now. So doesn't it look more like that?
Okay. Like a party hat.
That being the case, looking at my bounds of integration, let's talk about the rows. I said, let's talk about the rows.
We're still drawing a picture. So the rows are constant. No,
See, I disagree.
No, sorry, they range from 0 to the edge.
Yeah.
No,
0
there's
to
no
the,
edge. There's no edge.
Well, the
From
first
0
one
to-
will be a function of row, right?
just use
No,
words.
the cone goes out.
It'll be functions of row in the first one, right?
Oh, will we?
Or function for rows.
Yeah.
Whoa, 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 you guys, hold on. Look at my picture. I think the arrows range from 0 row value to the row value described by the
Circle.
plane,
Yeah.
the plane, z equals 1. Is it not true? Apparently, must be apparently. Well, look, I'm talking about everything below that plane, z equals 1, and above the cone. That's the region of which I'm integrating. So I think if I'm going to find extreme values for rho, which are going to be my lower and upper bounds of integration for the first integral, I think I need to talk about where all these arrows start, where their initial point is, what rho value is at the initial point, which is that. So I think the terminal point on all these arrows, but the terminal points lie on the plane. So let's talk about this plane in terms of rho theta to phi's. Isn't C nothing more than rho times cosine of phi, and it's equal to 1. Doesn't that just mean rho is
Secant phi.
thank you, secant phi. Well, let's talk about other variables. My next variable integration is going to be inevitably theta. So try to span out this three-dimensional object. How do your theta values range? 0 to 2 pi. What about the phis? 0 to 1?